Hello, this is Flava MCP Hubs. I will now begin the presentation. The presentation will be given by the two of us. First, if I may start, hello. From 2018, Line Plus created the in-house cloud Verta and the next generation platform Flava. I am Park Min Hyuk, currently the tech lead for the Flava MC Fair division. Hello, I am Inbei Kang, and I have been developing Verta and Flava in the same team since 2020. Currently, I am in charge of the backend for Flava MCP Pure B. First, I'd like to tell you what topics we'll be covering today. Today's presentation is divided into 5 main chapters. First, I will explain why we had no choice but to create MCP Hub and what kind of platform it is. Secondly, I will explain the structure we call the 4-layer backbone model, which is how the MCP hub actually operates internally. Third, I'd like to share how we bridge the protocol gap between standards and in-house authentication, which was one of the most challenging aspects among the 4 layers. Fourth, we initially used an open source gateway, but ultimately, this is a story about the process that led us to decide to build it ourselves. Lastly, we will share what has only become visible since this became a single platform, and the path that still lies ahead. Then, let's dive right into the first chapter. First, let's look at what Flava MCP Hub is and why we created it. MCP stands for Model Context Protocol. Then, what is Model Context Protocol? LLM is smart, but at the point where the learning is finished, my mind is blank. What is happening in our system right now? LLMs do not know what data has been accumulated. You have a good mind. This means we have no eyes to see what's happening outside, nor hands to act. MCP server is a standard that gives eyes and hands to LLM. LLM can directly access external tools and data, so it serves the role of allowing us to retrieve necessary context as needed. Now, we've briefly learned about MCP. Let's return to the main topic and talk about what the Flavors MCP Hub is. Flava is a private cloud commonly used within the company. And the MCP platform commonly used in the Warriors that went on top of Flava is the Flava MCP Hub. The identity of the Flavor MCP Hub can be expressed in 3 words: catalog, runtime, and Earth Gateway. First, the catalog serves to provide an at-a-glance view of what MCP servers are available internally. It eliminates the question of what MCP server can be used internally. The runtime makes it easy to create, deploy, and use MCP server directly. And finally, the Earth Gateway acts as an authentication gateway that allows for easy setup of permissions and access control. The Flava MCP server simultaneously takes on these 3 roles. So now internally, in actuality, let's take a look at how much it's being used. Let's look at the numbers MCP Hub has accumulated since the service launch. There are over 650 MCP servers running, more than 200 teams are using it, and the cumulative number of tool calls has exceeded 11.5 million. In fact, it quickly became the standard infrastructure within the company. However, I think you might not grasp the full scope of these numbers since they are just numbers. I have prepared a short demo. We have prepared 2 demos. The first is Flavor MCP Hub. Among various MCP servers, there is also Confluence MCP. Let's take a look at the TechVerse 2026 schedule using Confluence MCP. Secondly, we directly created a Kubernetes MCP server. I will demonstrate how to look up workloads in a specific namespace. What's surprising is that each of these two things takes only 1 minute. First, let's watch the demo video. We will now take a look. Hong Kong. Just a moment. The screen you are currently seeing is the Flava console. Let's now go into the MCP app. Then you will see a list of MCPs that can be used on this initial screen. And I will go into Confluence MCP. As you can see, there is a one-click install button. If you click this, VS Code will automatically launch, and the MCP server settings screen will immediately appear. If you press the install button here, the setup is immediately complete. About 15 seconds have passed. We were able to configure it quickly. I'd like to ask about the Tech Week schedule. Then, using the Confluence tool, LLM will generate an answer. Oh, the answer came right away. We provide MCP server in such a way that it can be used easily and conveniently in a short amount of time. And the second demo, as I mentioned earlier, is to create a Kubernetes MCP and then query the workload of a specific namespace. Let's take a look. This is this is the screen you saw earlier. I will create a Kubernetes MCP using a predefined template. Here, you enter the name. And since it is Kubernetes MCP, I will create an MCP server using the pre-prepared kubeconfig. Please wait a moment, and the MCP server will become active. This time, we also provide a playground environment where you can easily test, and you can try using MCP there. I will ask. We set up the MCP that we just created. I will ask to retrieve the cron jobs in a specific namespace. If you ask this way, you can see the LLM generate a response using the resource list tool itself. We provide a simple and convenient way to not only use MCP, but also to create, deploy, and finally use it. Let's now move on to how this easy-to-use platform actually works internally. However, before I show you the structure, I think it would be helpful for your understanding if we first go over the problem we initially had to solve. There were 4 issues we encountered while using MCP server internally. First, MCP server spread everywhere without control. Since each team created and used their own, no one knew what was running where. Secondly, the authentication methods were all different. Although MCP is powerful in context propagation, without proper access control, it can be a double-edged sword. However, having each team write authentication-related code directly was too costly. Thirdly, the in-house authentication could not keep up with the MCP server standard. We will discuss this in more detail in the protocol gap section later. Fourth, there was a complete lack of visibility. There was no data on who was using what or how much, so no one could make a judgment. To solve these 4 issues at once, we needed a common platform. So what we created is the Flava MCP Hub. We solved these issues using a 4-layer plumbing model. As the name suggests, it is structured with layers like pipes through which requests flow. Shall we trace a user's request once? As shown in the diagram, it starts from the client, passes through the connector and gateway, and reaches the MCP server at the very end. We have divided the responsibilities required for this flow into 4 layers. From the first floor connection, second floor proxy, third floor authorization to the fourth floor monitoring. Then, let's go up from the first floor in order. It is the first floor connection, where users first arrive. From the client's perspective, it's simply a matter of connecting using standard I-O. The connection is completed in a single line. However, the connector in the back. We are tackling a lot of complex tasks. The YDC flow token cache. When the token expires, it is automatically renewed, and the bearer header is also injected. It handles everything required for internal authentication. Thanks to this, the client is not even aware that they are attached to internal authentication. They just feel like they're connected to a normal MCP server. How this is possible will be explained in more detail in the protocol gap section later. I will explain it. Up. Moving up one level, we have the L2 proxy. Before the request received by the connector actually reaches the MCP server, this is where the policy is refined and determined for delivery. The core component is the MCP gateway. When the team deploys an MCP server, the gateway comes up with it, right in front of the server. Then, for authentication, CORS, header transformation, and transmission protocol, the gateway standardizes and processes all of these under the same protocol. Therefore, each team can focus solely on the MCP server logic without having to deal with anything else. Previously, each team implemented this differently, but now all duplication is eliminated as it's absorbed into this single layer of the gateway. So how is authentication handled in this gateway? The answer is the third layer, authorization. When the gateway receives a request, the first thing it does is token validation. The token has already been issued by the connector on the first floor. Gateway receives a token and verifies various in-house authentication methods in one place. Previously, we had to write separate authentication codes for each MCP server. However, now that the gateway only passes validated requests, the server does not need to worry about authentication at all. The fourth and final layer is the monitoring layer, which supervises the three preceding layers. From the client to the MCP server, we collect all tool calls, authentication results, and latency throughout the entire section into a single pipeline. Now you can see at a glance who called it, when, and with what tool. Until the arrival of the Flava MCP hub, internal MCP usage was completely invisible. As I mentioned earlier as a problem point, thanks to this impersonation, data began to accumulate for the first time, and it is now being used as input for our next design. We have thus reviewed the four-layer structure. Now, we'll delve a little deeper into one of the most challenging aspects, the gap between standards and internal authentication, which is the protocol gap. From here, Minyuk will continue the presentation. Thank you. When a user connects to the MCP server under the Flava MCP, they simply use their client. This was possible because we bridged this protocol gap internally. The gap between MCP server standards and in-house authentication. I will now show you how we connected the gaps. If you look at the screen, the left side is the MCP specification. To the right is our in-house authentication system. First, the MCP server standard on the left should be able to connect directly to the server that the client first encounters. Therefore, dynamic client registration like DCR and CIMD is a prerequisite. However, the internal authentication system on the right does not support such a standard. It is IM-based internally, and clients must be pre-registered, and tokens must also be obtained from the internal authentication system. In short, it's a structure that does not accept new clients. Therefore, there were two possible outcomes. If we follow the MCP standard as is, our internal authentication system will not be supported. If we create it to fit the internal authentication system, then it won't be compatible with the MCP server standard. This area, which cannot be aligned with either side of this dashed box in the middle, is precisely the protocol gap we encountered. So, this gap actually completely separates the client and the MCP server. If there were no MCP server hub, each team would have had to memorize these broken sections on their own. Each team separately implements MCP server authentication and creates browser callbacks, catching, and refreshing tokens. The same set of authentication codes. Each team had to rewrite it. There. Not only that, but each team also had to bear the operational responsibility for the code they developed. Ultimately, the same problems recur in each team within the company. This is not a problem for individual teams to solve, but rather, this was a problem that the platform had to solve at once. The solution we chose is actually surprisingly simple. It is like adding another layer between two disconnected worlds. One layer is the connector. It's the purple box in the middle of the screen. From the client's perspective, the connector simply appears to be a standard STD-IOMCP server. Whether it's Codex, Claude Code, or Cursor, they will connect to the STIO-MCP standard as they know it. However, internally, the connector takes on all the complex tasks of internal authentication. From internal OIDC browser, callback token cache auto-renewal, to bearer header injection. This one layer absorbs all the complexity required for authentication. So, by the time the request exits to the right of the connector, it has already been authenticated. It will flow towards the MCP server. This one line at the bottom of the slide best illustrates the core idea. The client is unaware of the existence of internal authentication. This is how the connector bridges the protocol gap. As a result, the complexity on the client side was completely eliminated. Each team no longer needs to worry about authentication, right? So the numbers change like this. In the past, to obtain MCP certification, each team had to understand the internal certification process. To apply authentication, it was necessary to design the authentication system. If these processes are carried out, it is expected to take about a week. However, now that the connector handles everything, the team only needs to focus on the MCP server logic. The rest will be handled by the Flava MCP hub. This kind of task would be completed in 5 minutes. This 5-minute difference in 1 week is what a single layer of connection has created. This bridges the gap between MCP standards and industry certifications. After the release of the MCP server hub, we faced another problem. We were using an open source gateway, but we faced limitations and consequently decided to switch to a gateway we developed ourselves. I will explain why we independently developed it during this process and what we were able to learn from it. Initially, to quickly configure the gateway for Flava MCP Hub, we began by directly using open source projects. At the time, the development period given was limited to about 2 months, so realistically, it would have been too burdensome to implement all the gateway functions from scratch. Therefore, we utilized an already verified open source gateway. We were able to quickly secure the basic functions and structure. Through this, we avoid re-implementing common problems that have already been solved. The requirements needed for the line channel platform, we were able to focus more on the integration. However, we encountered several limitations while directly using open source gateways. The first was the difference in language stacks. Our team had many members familiar with Go, but that open source project was Rust-based. It was difficult to analyze or debug failures. The second is the direction of open source and that internal requirements were not always correct. The open source's own goals and because there is a roadmap. It was difficult to reflect the necessary technologies or requirements at the desired speed. Third, there was the burden of managing forks and patches. To handle necessary changes in the internal authentication system as upstream issues or PRs. We had to manage it as a separate fork. In this process, I will introduce a few issues where it was difficult to use the basic open source software as is. The first was a JWS compatibility issue. Within the JWS key provided by the in-house authentication system, it contained a key that uses the ES512 algorithm, but the framework we were using at the time could not parse this value. Even if you don't use keys for the actual specific financial transaction verification, failed during the JW case loading stage. There was an issue where the gateway was not operating. The second issue was the execution order between course and the authentication middleware. If the authentication middleware operates before CORS and authentication is enabled, the browser's pre-flight request was rejected before receiving the CORS header, so it did not function correctly. The third issue was memory stability. During the process of handling MCP server traffic, the gateway frequently encountered OOM errors. This made it difficult to predict the operational stability of the MCP server. As these problems accumulated, we determined that we needed our own gateway that could quickly fix necessary functions and control them according to the operating environment. During the redevelopment process, we proceeded in a direction that would allow us to improve existing issues. First, we redesigned the gateway to meet internal requirements. We implemented it to allow direct control over the core operations of the gateway. Also, as we re-implemented it based on, it has become easier to analyze failures and debug using familiar languages and tools within the team. And as we no longer depended on upstream or forks, we are shortening the patch cycle, and we were able to quickly implement necessary feature improvements. Finally, based on these changes, operational stability and convenience have been improved. The lesson we learned from this experience is that while open source is a good choice for a quick start, it may not always be the right choice for our specific situation. Initially, we were able to reduce development time and quickly validate features by utilizing open source solutions. However, the goals that open source projects aim for. If the requirements for our operating environment keep changing, simply following along with forks or patches could increase the operational burden. In particular, with the recent ability to analyze and improve code using LLMs, the burden of direct development or migration has been significantly reduced compared to before. So rather than unconditionally replacing open source, we consider the direction of open source, and we believe that developing our own solutions in areas where our requirements are not met can be a choice that enhances long-term stability. Ultimately, what is important is not the open source itself. Could we directly adopt a foundation that meets our operational requirements? Now, I will discuss what we actually observed after implementing the piping in the MCP server hub. First, the value we expected was platform efficiency. If each team starts creating their own MCP server, connection methods, authentication processes, authorization management, and operational approaches would have to be repeatedly implemented by each team. The MCP server was created to handle this repetitive task on the platform. teams no longer need to recreate the same integration pattern every time. Internal authentication and access control can also be used in a common way. Additionally, operational elements such as the server's visibility ownership policy can be consistently managed. As a result, the MCP hub creates a new server to cover the operating costs. It served as a pipeline that enabled teams to adopt MCP server more easily. However, once we laid the groundwork and started operating, unexpected value began to emerge. As multiple MCP servers were connected through the MCP hub, all tool calls naturally passed through the hub. We can also see which tools are actually used frequently and which team's MCP server was reused by other teams. This data goes beyond simple monitoring. It became the basis for platform decision-making. For example, which features should be officially supported first? Which MCP server templates should be created? We can determine which features are important to actual users through traffic analysis. This means that initially, plumbing was installed to facilitate connections. After operations, the pipeline became an observation point for understanding the use of company-wide AI tools. The future direction is to further automate the remaining repetitive tasks in the process of introducing MCP server. The first is OpenAPI to MCP. Based on the OpenAPI specification, the direction is to enable exposing existing APIs to the MCP server. The second is internal Earth. API authentication that was previously implemented by each team. It is a feature that allows it to be used as is. The third is support for the latest MCP server specifications. As MCP server is a developing protocol, changes are frequent. Since the July 28th, 2026 version will be released soon, related changes will be implemented. Fourth is CLI and skills. Developers' actual CLI environment, or we plan to expand it so that it can be naturally used within the skill flow. The last one is IDJAG. This is aimed at automating token exchange and authority delegation between various systems to provide more secure and convenient cross-system access. Ultimately, the goal is to enable more teams to create, connect, and reuse MCPs. The platform takes on more of the burden of authentication and operation. I will elaborate on two related points. The first feature I would like to explain in more detail is OpenAPI to MCP. Many teams already have REST APIs. However, for an AI agent to use this API, currently, we implement a separate MCP server directly, or we need to implement the tool. OpenAPI to MCP. To address these issues, the goal is to streamline the process. It transforms the API paths and operations into an MCP tool based on the OpenAPI specifications of the REST API that each team possesses. This means exposing it as an MCP server endpoint. This means that existing REST APIs do not need to be re-implemented as MCP server. Our goal is to provide it like an MCP server that agents can use. Next is IDJAG. The direction of IDJAG is: this involves automating token exchange and delegated authorization within the platform. To use an existing MCP server, you must agree on the consent screen to grant the necessary permissions for each MCP server. We had to issue and use separate tokens for each MCP server. However, after IDJAG was introduced, you would be issued an IDJAG token. With this single token, you can exchange it for the necessary tokens at each MCP server and use it. Through this improvement, We no longer need to register and get consent for each MCP server or client as we did before. By exchanging tokens from the MCP server, they become interchangeable, which significantly increases usability. Thank you for listening to our presentation. Additional questions or discussions can be pursued at the Ask the Speaker session, so please feel free to attend. Thank you.